All right, let's dive right in. We're going to talk about something that's at the absolute heart of every modern computer, the processor. It's the fundamental building block that makes pretty much everything you do possible, from browsing the web to playing music at the same time. So, that leads to the big question, right? The one we're going to unpack in this whole explainer. How on earth can your computer, which might only have a handful of CPU cores, juggle dozens, maybe even hundreds of different apps at once without them all just crashing into each other? The answer, as you might guess, is all about the operating system. To really get why this is so important, just try to picture a world without a proper operating system. It would be total digital chaos. One program would just run, hugging every single resource until it decided it was done. And if it crashed, the whole machine would crash and burn right along with it. The OS is what brings order. It creates this system of controlled, safe sharing, which gives us isolation and true multitasking. And the hero of this story, the key idea that brings order to that chaos, is the process. Put simply, a process is just an instance of a running program. It's the active, living, breathing version of the software you just launched. And this difference, it's everything. A program is just a file sitting on your hard drive, totally passive. It's like a recipe on a piece of paper. But the moment the OS loads it into memory and tells the CPU to start working on it, bam, it becomes a process, an active thing with resources and a purpose. Okay, so what's actually in a process? What's it made of? Well, it's not just the program's code. Think of it like a complete care package for your program to run in. It gets its own private slice of memory, it gets the current state of the CPU's registers, a list of any files it has open, its security permissions, the whole shebang. It's a self-contained little universe. And this leads to a super clean way to think about it, especially if you're ever in a technical interview. A program officially turns into a process the very moment the operating system gives it the things it needs to live: CPU time to think, memory to exist in, and resources so it can talk to the rest of the system. Okay, but that brings up a bit of a puzzle, doesn't it? We know a single CPU core can really only do one single thing at a time. So how in the world does it create this illusion that it's running your web browser, your music player, and your word processor all at the exact same time? Well, the secret is this really clever trick called time slicing. The OS acts like the world's fastest traffic cop. It lets process A run for a tiny, tiny fraction of a second. Then it hits pause, saves everything it was doing, and lets process B have a turn. Then process C, and so on, cycling through them thousands and thousands of times every single second. And that's the magic right there. It's an illusion, because the switching happens so incredibly fast, I mean faster than we can even perceive, it creates this seamless feeling that everything is running in parallel, and that is what we call multitasking. So that act of switching, of stopping one process and starting another, it has a technical name. It's called a context switch. This is where the OS has to meticulously save the entire state of one process. Its context. Then load up the state for the next one and let it pick up right where it left off. But here's the catch. All this switching isn't free. Not at all. Every single context switch costs something. It burns up CPU cycles that aren't being used for your actual work. It messes with the CPU's super fast memory, the caches, and if you do it too much, it can actually slow the whole system down. So to manage this constant juggling act, the OS has to keep track of what every process is doing at any given moment. A process isn't just on or off. It can be running, actively using the CPU, or it might be ready, which means it's good to go, but just waiting in line for its turn, or it could be blocked, maybe waiting for something slow, like a network request. And then finally, it's terminated when it's all done. All right, here's another piece of interview gold, a really subtle but super important detail about how systems like Linux actually work. You might think you just start a program, but that's not quite right. What the OS really does is it first creates a brand new empty process, and then it loads your program's code into it. It's a small difference, but a powerful one. And this happens with this kind of elegant two-step dance. First, a system call called fork creates an almost perfect clone of the current process. Then, a second call, execv, comes in and completely replaces the guts of that new child process with the program you actually wanted to run. It's a really powerful model. So we've talked about how processes can be kind of heavy, right? They're expensive to create and to switch between. So you might be asking, is there a lighter way to do things? And the answer is yes. It's called a thread. A thread is the smallest unit of work you can have inside a single process. And this table really gets to the heart of the matter. It's the fundamental trade-off. With processes, you get really strong isolation. They're in their own little sandboxes with separate memory, which is safe, but that safety net is heavy. It comes with high overhead. Threads, on the other hand, all share the same memory. This makes them super lightweight and fast to switch between, but it also means that if one thread messes up, it can bring down the entire party. So at the end of the day, this is the choice that engineers are making all the time. Do we go for the bulletproof safety and robustness of separate processes, or do we go for the raw speed and efficiency of shared memory threads? It's all about picking the right tool for the job. And really, that's what this is all about. Building amazing, complex systems isn't about just picking the fastest thing or the safest thing. It's a balancing act. You're constantly juggling isolation, performance, and just how complex you're willing to make your design. Okay, so if you're going to walk away with one single sentence that wraps all of this up, maybe to ace that interview question, it would be this. A process is the operating system abstraction that allows programs to execute safely by encapsulating CPU state, memory, and resources, while the OS time slices the CPU between processes using context switching. Nailing every part of that sentence means you've got a rock-solid understanding of this. And that leaves us with one final thing to think about. Now that you know all this, how would you design something really complex, like a modern web browser? You need it to be blazing fast, but you also need total safety, right? You can't have one bad website in a tab crash your entire browser. It's a really fascinating problem, and it's exactly the kind of challenge that engineers are solving every single day.